Hello everyone, I'm Ziyan Wang. Today I'm going to present our paper, Variational Imbalanced Regression, Fair Uncertainty Quantification via Probabilistic Smoothing. Here is our motivation. Suppose we have a human dataset, and the features are representing various physiological data, and the output is a continuous value indicating the side effects experienced from some certain drugs. The yellow line here is the age distribution for this dataset. Note that the dataset is imbalanced, with a substantial number of samples in the 25 to 45 age range, while on those infants and the elderly are sparse. Now, in such scenario, a deep regression model is trained and we are likely to encounter three cases. First, for the age groups with ample data, such as those between 25 to 45, the model is expected to yield low error with low uncertainty, which is perfect and what we expected. For the age groups that are minorities, we may either have the case that it shows low error with high uncertainty, which indicates that the model is underconfident since the limited data, or it shows high error with low uncertainty, which means the model is overconfident. This example shows the importance of designing novel algorithms to make reliable predictions and uncertainty quantification when the training data is imbalanced. Now, I will introduce our methods. Our approach introduces a novel assumption termed NID, neighboring and identically distributed, which differs from the common IID assumption in most deep learning models. Under the IID assumption, each latent data is only influenced by its original data point. In contrast, our NID assumption asserts that each latent data is influenced not just by its original data point, but also by neighboring data points. As illustrated in the figure on the right, if we consider Py to be our latent distribution, and Y is a corresponding label for each latent data. Then, after applying some kernels to smooth this distribution, we will have a reweighted curve, and P tilde, and we can observe that the original minority get enlarged, which will increase the confidence in the model predictions. That is our first method. Now, given the reweighted latent feature we have, we generate the pseudo-count, pseudo-mean, and pseudo-covariance. Next, based on these pseudo-parameters, we are able to calculate the posterior parameters of the normal inverse gamma distribution. In the end, we can further obtain the mean and the covariance of our results, while the mu is the prediction and the sigma is the uncertainty quantification. And note that the pseudo-count here will be reweighted similarly as we did in the feature space to increase the confidence for the model prediction. We also showed a generalization bound and proved that after reweighting the original propensity P to P tilde by using our VIR estimator, although it will increase bias, but it will significantly reduce its variance in the imbalanced setting, thereby leading to a lower generalization error. And the results show that our methods outperform all the baselines for both accuracy and uncertainty quantification. In this work, we identify the problem of probabilistic deep imbalanced regression. We propose VIR to simultaneously cover two desiderata, balance accuracy and uncertainty quantification. We also show that VIR can achieve better generalization bound. The code will be available soon.